These are examples from Lesson 2-3, Laws of Logic and Definitions. In this video, you will learn what a biconditional is, how it relates to a good definition, and what constitutes a good definition. You will also use the laws of detachment and syllogism to draw conclusions in geometry and logic. Example 1. In this example, you will learn how to write a biconditional statement. Write a biconditional in two different ways, given the provided conditional statement. Are both the conditional statement and converse for it true? And here we have this statement. If x plus 5 equals 8, then x equals 3. So here we have a conditional and it's an if-then form. So to write a biconditional statement, we take the hypothesis, which is here, and the conclusion, which is here. This is P and this is Q. And instead of the conditional form, if P then Q, we're going to write it in this form. P, if and only if, Q. So we would write x plus 5 equals 8 if and only if x equals 3, Q. Each biconditional should be able to be written in the other way. So we take the Q and the P, switch those out. Q if and only if P. So we can write x equals 3 if and only if x plus 5 equals 8. And there you have two biconditional statements. It asked, are both conditional statement and converse for it true? And so if x plus 5 equals 8, then does x have to be 3? Yes, that's the only value for 3, so that's true. And for the converse, if x is equal to 3, that's what you're given, then is it true that x, that 3 plus 5, is going to always equal 8? Yes, it's true. So both of them are true. Example 2. In this example, you will learn to find the conditional and its converse from a given biconditional. Write a conditional and converse from which the following biconditional came. Then write the biconditional in another way. A polygon is a quadrilateral if and only if it has 4 sides. So as you can see, this is a biconditional. It has the if and only if statement here. So this would be P. This would be Q. It has 4 sides. And the if and only if imply biconditional. So for a conditional, we in if-then form, if P then Q, we have if a polygon is a quadrilateral, comma, then Q, it has 4 sides, period. The converse, we take Q, write it first. We're using Q, if Q, then P. So if it, what's it? A polygon. So if a polygon has 4 sides, then the hypothesis, it, the polygon, it is a quadrilateral. And then they asked us to write another biconditional in another way. So here we have P if and only if Q. All we have to do is write it in the reverse order. Q if and only P. So we're going to start with the Q, and we're going to start off with a polygon instead of if a polygon. So a polygon has four sides if and only if the polygon, it, is a quadrilateral. Example 3. In this example, you will determine if a statement is reversible. For a statement to be reversible, it must be a true biconditional. That is, it's conditional and its converse, they both have to be true. So we have to check for that. Look up and write down the definition of angle bisector as a complete sentence. So that's the first thing we do. You can look it up in your notes. You can look it up in a math dictionary. But it needs to be a complete sentence. So the definition for angle bisector, we write it down. And I looked it up, and my definition says an angle bisector is a ray that divides an angle into two congruent angles. Now, to write a conditional from this definition, from my definition here, we need if, we need then, an if-then form, so we need to take our hypothesis. If we've got an angle bisector is a ray that divides an angle into two congruent angles, you can see how it's cut into two parts. The condition is if a ray is an angle bisector. So if a ray is an angle bisector, comma, then the conclusion, that ray, divides an angle into two congruent angles. Then it divides an angle into two congruent angles. So there's our conditional if P then Q. For our converse, we just switch it around and take the conclusion and make it our hypothesis and vice versa. So here we have, if we had this one here, our hypothesis now becomes the conclusion and vice versa. So it divides an angle into two congruent angles. What's it? A ray. So if a ray divides an angle into two congruent angles, comma, then we go back to the hypothesis and make it our conclusion. Then the ray is an angle bisector, or it. Then it is an angle bisector. Okay, it's asking us if this is reversible. That means both of these are true. If a ray is an angle bisector, then doesn't it divide an angle into two congruent angles? Yes, it does. If a ray divides an angle into two congruent angles, then is it called an angle bisector? Yes, true. So both of those are true. This is reversible. Because it's reversible, we write a biconditional. So the biconditional, you can write it either way. I like to write from the conditional, I like to use the hypothesis from that one, but you can do it either way. So the biconditional here would be a ray is an angle bisector and then if and only if that ray or it divides an angle into two congruent angles. So an array is an angle bisector if and only if it, the ray, divides the angle into two congruent angles. Example 4. Okay, for example 4, you learn to decide whether statements are good definitions or not. To be a good definition, remember that there's two criteria for a definition to be good. First, it must be clear and precise, and second, it must be reversible. We just talked about reversibility. So, example 4, which of the following choices is a good definition based on the requirements for one? Explain why or why not each is considered good. So we'll go through each one of these systematically. Choice A fish is an animal that swims. Okay, so we want to determine whether this is a good definition or not. Let's see if it's reversible. If an animal is a fish, then it swims. That's true. If an animal swims, then it is a fish. Is that necessarily true? No, it's not. It could be a whale. Whales swim. It could be a dog. Dogs can swim. So this would be, we'd write something like not good. And then we can say not reversible, since other animals besides fish swim. Okay, B. Rectangles have 4 sides. Let's see if it's reversible. If a figure is a rectangle, then it has 4 sides. True. If a figure has 4 sides, then it's a rectangle. Well, not necessarily true. You can have a 4-sided figure that is not a rectangle. For instance, it could be a parallelogram, or it could be a trapezoid. It has 4 sides. It's not a rectangle. So this is not good, not reversible, and by the way, this is also not very clearly written, and it's not precise enough, because rectangles not only have 4 sides, they have 4 right angles also. So you could use either reason for that. I'm going to say it's not reversible and not clearly precise. Choice C. Giraffes are animals with very long necks. Okay. This time I'm going to start with seeing if it's clear and precise. Giraffes are animals with very long necks. How long? How short? So this isn't very precise. It doesn't give us a description of how long the neck is. So not good. Not precise. Okay, and it's also, let's see, is it reversible? If an animal is a giraffe, then it has a very long neck. That's true. If an animal has a very long neck, then it must be a giraffe. Not necessarily true. It could be an ostrich. So, and not reversible. Choice D. A penny is a coin worth 1 cent. Let's see if that's reversible. If a coin is a penny, then it's worth 1 cent. That's true. If a coin is worth 1 cent, then it's a penny. And that's going to be true because we're going to assume that we're in the United States here. So there are probably other coins worth 1 cent in other countries, but we're going to assume this is true. So it is reversible. Now, what about precise? A penny is a coin worth 1 cent. It tells us exactly what it's worth. It tells us it's a coin, and it's called a penny. So this is a good definition. Is precise, clear, and reversible. Okay, example 5. In this example, you will learn how to identify when and how to use the law of detachment. Now, many students find the law of detachment a little confusing at first because in reality, it's a pretty simple law, but it's so simple sometimes we overlook what it's saying. To use the law of detachment, the hypothesis of a given conditional has to be equivalent to the statement that I give you so that you can make your conclusion. So let me go through this systematically. Example 5. What can you conclude from the given true statements? State which law of logic has been applied. Okay, statement number 1. If a student gets an A on a final exam, then the student will pass the course. So there's our given conditional. And then we're given a second statement. Felicia got an A on her history final exam. So I'm going to go through and use P, Q's, and R's so we can make sure that we get this right. This is a conditional with if and then. So I'm going to let a student gets an A on a final exam be our P. And then after the then, our conclusion, the student will pass the course, will be our Q. So if P, then Q. There's our conditional. Now over here we've got a third statement. Felicia got an A on her history final exam. This whole thing, I'm going to call it statement R. Now, for us to be able to use the law of detachment here and make a conclusion to this based on this, P must equal or be equivalent to R. Let's take a look. If a student gets an A on a final exam, Felicia got an A on her history final exam. Okay, a student was Felicia. She got an A, and it was a final. So they are equivalent. If they are equivalent, then you can create a conclusion to where R, if R, then S. But the S has to be equivalent to Q, this conclusion here. So based on the conclusion here, we can write our conclusion here. So what we're going to write for S is based on the fact that Felicia got an A on her history exam, we take this part. The student will pass the course. We can put it in terms of Felicia. Then Felicia will pass not just a course, but pass her history course. So if you're asked to write a conclusion as a statement, then you write the whole thing. If R, then S. If Felicia got an A on her history final exam, then she, I'll use she for Felicia, will pass her history course. And so which law did we use? We used the law of detachment. Example 6. In this example, you will see how the law of detachment works and how it doesn't work in different situations. Now, in this video, I've only included part A. Part B is written out and filled in the field notes provided in Schoology. So if you need that one, you can look at that one. Part A. What can you conclude from each of the given statements in their additional statements? Part A. Given, if a ray divides an angle into two congruent angles, then the ray is an angle bisector. We had this earlier on in an earlier example, but I've gone ahead and drawn this out to kind of help you see what you're doing. If they don't make a drawing, it's always a good idea to go ahead and make your own and label it. So if a ray divides an angle into two congruent angles, then the ray is an angle bisector. That's just the definition of angle bisector. Then they give us a statement. Ray RS, right here, divides angle ARB, divides it so that angle ARS is congruent to angle SRB, this one right here. So all they're doing is they're redescribing the definition of angle bisector. So let's see if we can do something with these two statements. We have if a ray divides an angle into two congruent angles. So I'm going to let this be P. We have if P, then the ray is an angle bisector. This will be Q. So if P, then Q. And then this is a brand new statement. Ray RS divides angle ARB so that angle ARS is congruent to angle SRB, and we're going to call that R. Okay, let's see if we can use the law of detachment here. If P, then Q, and then we have R. Let's see if we can equate R and P together, see if they're equivalent to each other. If a ray divides an angle into two congruent angles, ray RS, ray, divides an angle would be angle ARB, so that, or into two congruent angles. The two congruent angles are these two, and they're saying they're congruent. So yes, P is equal to R. We can use the law of detachment, and we can write R, if R, then S. But we have to make sure that S, the conclusion to this, is based on the conclusion to the first statement. Then the ray is an angle bisector. So take the second part, and in terms of what we have here, rewrite it. So if ray RS divides this angle into two congruent ones, then the ray, which is ray RS, is an angle bisector. So ray RS is an angle bisector. So we can write the conclusion statement as a conditional by using R and S. So if ray RS divides angle ARB so that angle ARS is congruent to angle SRB, comma, then the conclusion S, ray RS, right here, is an angle bisector. And we use the law of detachment here. The law of detachment won't work unless the conclusion to that first conditional is equivalent, or excuse me, the hypothesis is equivalent to the hypothesis or the statement that's given to you second. So be careful, they have to match. Example 7. In this example, you will make a conclusion based on a law of logic given several conditional statements. What can you conclude from the given true statements? State which law of logic is applied here. Statement number 1. If a figure is a square, then it is a rectangle. Statement 2. If a figure is a rectangle, then it has 4 sides. And they want us to make a conclusion statement. So, given our two statements here, let's go ahead and break them down into our logic symbols here. If, then, this is a conditional. If the hypothesis, a figure is a square, let's let that be P, then Q, which is it is a rectangle. What is it? It is the square. Now, notice that the conclusion here, it is a rectangle, is the same as the hypothesis here. If a figure is a rectangle, these are the same. So let this be Q. It's the same as this. Then it has 4 sides. It has 4 sides. It's not like any of the others. It's going to be R. So we have if P, then Q, and we have if Q, then R. Do you see the chain it's creating? That means we can use the law of syllogism. anytime statements connect like that. And so, our conclusion, we would take our very first hypothesis and our very last conclusion that's been connected, and we'll write if P, then R. So if a figure is a square, comma, then R, it has four sides. Then that square has four sides. Then it has four sides. If a figure is a square, then it has four sides was based on these two statements, the conclusion statement, by the law of syllogism. Example 8. In this example, you will see how the law of syllogism works and how it doesn't work. When using the law of syllogism, the conclusion of one conditional must be equivalent to another conditional's hypothesis, just like we talked about a while ago in example 7. So here we go to example 8. What can you conclude about the given statements? Here we have two statements again. Here's the first one. If you do gymnastics, then your body is flexible. Here's our second statement. If you do ballet, then you are flexible. Okay, well, some of you can probably already see it, but let's break it down. We have an if-then statement here, a conditional, so we're going to let if P is you do gymnastics, then Q is your body is flexible. Now, the hypothesis here, you were hopefully expected it would talk about a body being flexible, so we can use the law of syllogism, but we can't because the hypothesis in our next statement or another statement is not Q. It's totally different than either one of these. So it would be R. If R, then you are flexible. Your body is flexible. These are the same. So if P, then Q, and the second one is if R, then Q. Well, this does not fit the law of syllogism because the law of syllogism requires the conclusion of one to be the hypothesis of the other, and that's not happening anywhere here. Even though these two conclusions are the same, that has nothing to do with the law of syllogism. So, cannot use the law of syllogism since Q is not a hypothesis of one statement and a conclusion of another. Example 9. In this example, you will see how the law of syllogism can involve more than two conditionals. What can you conclude about the given statements? This time we have three statements. I'm going to read them through pretty quickly. If a triangle is a right triangle, then it contains exactly one right angle. Statement 2. If the right angle measures 90 degrees, then the sides that form that angle are perpendicular. Statement 3. If a triangle contains exactly one right angle, then the right angle measures 90 degrees. Well, there's a lot of statements that look like they connect with each other, but not necessarily in the order we would like them. So before we decide to use the law of syllogism or not to use it, let's see if it works. Let's see if the law of syllogism works. Let's start with the first one. If a triangle is a right triangle, a triangle is a right triangle, let's let that be P. So if P, then Q. It contains exactly one right angle. So if P, then Q. Now, instead of just immediately going to the second statement, let's look for a hypothesis that will match this conclusion right here and see if we can chain them together. It contains exactly one right angle. If you look at the second statement, it it doesn't start with a hypothesis that talks about containing exactly one right angle, a triangle containing one. So let's skip this one. This one says if the right angle measures 90 degrees. So go to the third statement, look at this. It says if a triangle contains exactly one right angle, it contains exactly one right angle. Those match. So if a triangle contains exactly one right angle, this is Q again. So this time we have if Q, but it's in our third statement, not our second. Then the right angle measures 90 degrees. This is something we haven't had previously. It's not P, it's not Q, so let's call this R. So if P, then Q, and then down here in the statement 3 we have if Q, then R. Now let's see if this conclusion matches with the hypothesis of what's left. The right angle measures 90 degrees. If the right angle measures 90 degrees. So that's perfect. We can use the law of syllogism here. That means if we have if Q, then R, R appears up here in the hypothesis. If R, then, and then the sides that form that angle are perpendicular. That's a brand new statement. So we'll call this S. So if a triangle is a right triangle, then it contains exactly one right angle. If a triangle contains exactly one right angle, then the right angle measures 90 degrees. And if the right angle measures 90 degrees, then the sides that form that angle are perpendicular. So using the law of syllogism, the chain law, so to speak, we start with our very first hypothesis and we end with our very last conclusion. So this would be if P, then S. So right here, if P, then S. So if P, which is a triangle is a right triangle, if a triangle is a right triangle, comma, then we go all the way back over to S. Then the sides that form that angle are perpendicular. Then the sides that form that angle are perpendicular. In other words, you've got a right triangle here, and they're saying if a triangle is a right triangle, this is a right triangle, then the sides that form the right angle here, here's the right angle, are perpendicular. So that would mean this side's perpendicular to that one.